Let's do one more example of a polynomial inequality, and then we'll jump into the rational inequalities. All right, so here is our inequality. Well, we need to get 0 on one side, so I'm going to subtract x from both sides, and I'm going to subtract 3 from both sides to get 0 over here. And that would give me x to the third plus 3x squared minus x minus 3 less than or equal to 0. Now we have it in the standard polynomial inequality form. So now I can state that this part, the left-hand side, the polynomial, is my f of x. You can't just choose this left side or the right side to be f of x. You need to get 0 on one side first, and then the other side will be f of x. All right, well, what do I have to do here? I need to factor this. Now, this one looks like it will factor by grouping. Now, I'm going to explain why. I think I've already done this, but you know it'll factor by grouping these two and grouping these two. If the coefficient here, think of this coefficient as 1 and this one 3. Think 1 over 3, the fraction, 1 over 3, is equal to this fraction, coefficient over coefficient, negative 1 over negative 3. So I know factoring by grouping will work. So if I factor the first two, I'm going to pull out an x squared. And it gives me an x plus 3. And then in order for this one to give me an x plus 3, I have to put a minus sign in front of it right there, right? Distribute the minus through and you get a negative x minus 3. All right, so that's f of x. So I'm going to factor, there's two terms, and I'm going to factor the x plus 3 out of both of those terms. And what am I left with? Don't simply say x squared, because there is a negative 1 right here. Right? If you want to put the 1 there, you could. So it's going to be x squared minus 1. One more step and we're done factoring. We just have to take care of this difference of two perfect squares. So we have x plus 3, x plus 1, x minus 1. And we're set. Remember what we have to do now. We're finding the boundary points. So I need to set it equal to 0 in order to get my boundary points, which I'll plot over here on the number line. So we simply do that, and we'll get negative 3, negative 1, and 1. These are my boundary points. They also happen to be the zeros, the x-intercepts, the roots of this function, this polynomial. All right, so let's see. Negative 3 goes first. Then I'd have negative 2, negative 1. Then I'd have a 0. Then I'd have a 1. Okay? Now what do we do? I need to know which regions to shade. And by the way, how many regions do we have? If I have 3 boundary points, I've got 1, 2, 3, 4 regions where I have to choose a test point. So maybe I'll call them TPs, test points. I will choose, you can choose anything to the left of negative 3 that you want. You could pick a negative 58.657 if you want to. I'm going to choose one integer to the left, negative 4. And in between here, there's only one integer in between. That would be a negative 2. In between here, I think that's a no-brainer. We choose 0. And then to the right of 1, let's just pick 2. Those are my test points. And I need to compute f of all of these. And what I'm looking for in particular is when it's less than 0, because if it is less than 0, I'm going to shade it. I know it won't be equal to 0 because the only numbers that would give you an equal to 0 are these test points. I mean, not the test points, the boundary points, -3, -1, and 1 that we computed down here. Okay, so f of -4. Well, let me see. I think it's going to be easier for me to plug -4 into this version rather than going x cubed, which would be -64. The numbers get pretty big. This is f of x right here too. So -4 and 3 is -1. Here we have -4 plus 1, which is -3. Here we have -4 minus 1, which is -5. And really, all we care about is it positive or negative? And what is this? When you multiply 3 negatives, you get a negative, right? I'll go ahead and write equals -15, but what we care about is it's less than 0. So if I plug -4 in to this polynomial inequality, I will get -15 here, so that is less than or equal to 0, so that's a good one. As a matter of fact, I will go make a note of that right now by shading the region that contains -4. That one's a good one. Let's now go to f of -3. And for -3, let's plug it in here again. No, I'm sorry, -2. -3 is a boundary point. -2. So -2 plus 3 is 1. -2 plus 1 is -1. -2 minus 1 is -3. So this turns out to be a positive 3, which is bigger than 0. Do not shade that region. We're only shading the ones that are less than 0. So then we go to the next one. We chose 0 for the test point, and that's really easy to plug in right here. 0 plus 0 minus 0 minus 3. F of 0 is a -3, which is less than 0. That's a good one. So if we plug in a 0 here, we get a negative number. It's true that that's less than 0, so the region that has -3, we shade. Okay? And the last one, f of 2. 2, I guess I can plug it in up here. 2 cubed is 8, plus 4 times 2 squared is 12. Minus 2 minus 3, that's definitely positive, but it looks like it would be 20 minus 5. I think I get positive 15, you can double check, but I know it's greater than 0. So we do not want to shade, because when you plug in a 2 into this polynomial, you get a number that's bigger than 0. So do not shade that one. So this would be, on an exam, half of your answer. The other half would be writing that in interval form, which I'll put a negative infinity there, I'll put a positive infinity over there, make it a little easier. So we're going to have negative infinity to 3. Oh, last thing. I need to check the boundary points. Are they open or closed? Do I fill them in or not? And I do. I need to. I haven't done it yet. Because it's less than or equal, -3 actually works. You plug in a -3, you're going to get a 0. And 0 is less than or equal to 0. Same with -1. Same with the other 0, which is 1. So the other way to write the solution is negative infinity to -3 with square bracket. Remember, we never put a square bracket on an infinity, positive or negative. And then we have one more interval, -1 to 1. So every single number in either one of these intervals, when plugged into this polynomial inequality, will work. So we'll either get negative numbers or 0 on the left-hand side to make them less than or equal to 0. And all the numbers not in these two intervals will give us something bigger than 0. Okay, now I'm going to make one comment here. In many of our examples, if you shade this region, you do not shade the next one. And then you shade one, and then you don't. It is not always like that. Absolutely isn't. So really, you need to put a test point in, you need to test a point in all 4 of the regions in this example. Okay, so now we're going to jump into solving rational inequalities, which could possibly be a little simpler than what we just did. And I'm only saying that because in our rational inequalities, we're never going to have something this complicated as a numerator or a denominator. It's usually much simpler polynomials for the numerator and denominator. Okay, so solving rational expression inequalities is similar to solving polynomial inequalities. The difference is that we set both the numerator to 0 and then set the denominator to 0, do it separately, solve each, and you find the boundary points that way. Okay, so in our first example, I can already tell when I solve the top, I'm just going to get 1 boundary point. When I solve the bottom, I'm going to get 1 boundary point. So for this one, we're going to have only 2 boundary points. All right, so let's solve and graph the solution set. Well, fortunately, it's already in a good form. We have 0 on one side. So first, set the numerator to 0 to find, what does that tell you? When you set the numerator to 0, we would be finding the roots, or the zeros, of the polynomial. When we set the denominator to 0, what are we finding? That would be considered the points where the function is not defined. To find points where f is undefined. All of these are the boundary points. So very simply, set the top to 0, set the bottom to 0. So I am going to make one note. Since I don't have any room to really put it over here, f of x is equal to 3x plus 3 over 2x plus 4. All right, and the inequality is taking f of x greater or equal to 0. Okay, start with boundary points. 3x plus 3 equal to 0 means 3x equals negative 3. All I did is subtract 3 from both sides. And now we're going to divide by 3. And we get x equal negative 1. That is 1 boundary point. Let's find the one other boundary point by setting 2x plus 4 equal to 0. So 2x is equal to negative 4 because we subtracted 4 from both sides. And then we divide both sides by 2. And we get x equals negative 2. So these are our 2 boundary points. Let's put a negative 2 there, put a negative 1 there. So how many regions did that break the real line into? 1, 2, 3. So we have to choose 3 test points. So 3 test points. Well, how about negative 3? And don't start complaining here. Look what we have in here. Do we have any whole numbers in between, any integers in between there? Nope. So it looks like we're going to have to choose negative, say negative 1.5. How about that? Which is negative 3 over 2. And then on the right of this, well, now we can pick 0 right here. So that is our 3 test points. Now we're going to plug them in. So we're going to say f of negative 3. Let's figure out if that's going to be, if it's greater than 0, we'll shade it, this region. If not, we will not shade it. So what are we going to get? 3 times negative 3 plus 3 all over 2 times negative 3 plus 4. Upstairs, we get negative 9 plus 3, which is negative 6. Downstairs, we get negative 6 plus 4, which is negative 2. That's equal to 3. That's bigger than 0. Is that what we're looking for? We want it to be bigger? Indeed we do. So, that's a good one. This is one we shade. Okay, now let's try negative 3 halves. So we're going to get f of negative 3 over 2. This will be good practice for you if it's been a while since you've worked with fractions. Negative 3 over 2. So it goes 3 times negative 3 over 2 plus 3 over 2 times negative 3 over 2 plus 4. Well, I like the denominator. Notice that this is 2 over 1. The 2's cancel and give us negative 3. So multiplying these two gives us negative 3 plus 4 gives us a 1, so it's really not even a fraction. Upstairs, we get 3 over 1 times negative 3 over 2, negative 9 over 2 plus 3. Is this positive or negative? Well, negative 9 over 2 is negative 4.5. Negative 4.5 plus 3 is negative 1.5. So that's negative 3 halves. Interesting. F of negative 3 halves is equal to negative 3 halves. This is less than 0. Therefore, no, we do not shade it. All right, the last test point is 0. And I don't think I need to do much work for this. Let me go ahead and write it down here. I think we can do it in our heads. Plug in 0 to f of x and see what you get. X is a 0, x is a 0, so the 3x goes away, 2x goes away, and we get 3 over 4. And that's bigger than 0. And that's what we wanted it to be, so we shade this region. So this is half of the answer. We solved it. We graphed it. Well, we graphed it, but now we need to write the solution. Whenever it says graph the solution set, we want to write it in interval form. So it'll just be taking this interval that's shaded, union, this interval. Oh, did I check the boundary points yet? No, I didn't. And this is a bit of a challenge. Should I fill in the circles? It's greater than or equal, right? Okay, so what happens when what were our zeros? Negative 1 and 2. When I plug in a negative 1, does this work? Is it true? Negative 1, it would be a negative 3 plus 3, so that's a 0 over whatever. So that's a 0. Greater than or equal to 0? Yeah, 0 is greater than or equal to 0. So negative 1, shade it. But what happens when I plug in the other boundary point? Negative 2 is the x value that made the denominator 0. Is a denominator ever allowed to be 0? No, it wouldn't even be in the domain of the function f. F of negative 2 would be, the denominator would be negative 4 plus 4 for 0. So negative 2 you can't even plug in. If you're not allowed to plug it in, if it's not in the domain of the function, it could not possibly be a solution, so you must leave that an open circle. So when you have polynomial inequalities that we did earlier with no fractions at all of the boundary points are either going to be all filled in or all open. But in a rational inequality, well, let me start with this. If it were a strict less than or a strict greater than, these would all be open circles. But when you have the equals part of it, greater than or equal or less than or equal, the bottom is going to fail. The boundary point you obtained by solving the denominator, setting it equal to 0, though that must remain open. Okay, so that's something that you must remember. And you'll always do it if you were to plug the boundary points back in to see if they work. Okay, the ones that work you shade, the ones that don't you leave circle. So written as an interval, we would say it's negative infinity to negative 2 with parentheses, union with a square bracket interval, negative 1 to infinity. This is the solution written in interval form. This is the solution written in graph notation.